Well, welcome everyone to the 2022 IDA Innovation Awards webinar. My name is Rob Thornton. I'm the president and CEO of IDEA, International District Energy Association. I'll be the moderator for today. Next slide, Tanya. Before we begin, a little bit of housekeeping. The webinar format will have three presentations, and that'll be followed by Q&A. We'd ask that you submit your questions in the Q&A box at the bottom of the screen. Please don't confuse the chat and the Q&A. We'd ask that you put your questions, as they come to you, put them in the Q&A box, but we're going to conclude all three presentations first in sequence, and then we'll have time for the moderated Q&A segment. The webinar will be recorded, and a link will be made available to all participants so that you can review and or share among colleagues or clients at your leisure. So again, please submit your questions, and then the webinar is slated to last 1 hour, but it's likely, actually almost certain, we'll have extra time. So we'll continue as long as the questions continue to flow in. Maximum would be 20 minutes long, an hour and 20. Tanya, next slide, please. So the Innovation Award, IDEA Innovation Award, was really started in 2013. It was the brainchild of Joe Brillhart, formerly of Johnson Controls. And Joe, I think was often impressed by the quality of the submittals for the IDEA System of the Year Award, but he thought, wouldn't there be some benefit to demonstrating how IDEA systems and our business partners are collaborating, solving problems, deploying technologies. And so the Innovation Award is intended to showcase really the partnering that occurs within IDEA, within our members. Last year, we had a variety of submittals. Tanya, next slide, please, if you would. Last year was really one of the most significant sets of submittals we've had. The submittals are judged by a panel of IDA members, really from a variety of segments. And the criteria is the application must be, show some ingenuity, basically a new practice or technology. Measured success, we ask that the results be actual, not aspirational, right? So the technology or the service should be actually demonstrating some benefit for perhaps like a 2-year time period. The innovation should also be replicable, not just a one-off solution, isolated, but something that can be replicated in many venues or globally. And finally, the submittals are judged on their economic and environmental benefit, like what advantages do they actually produce. So this is the scoring criteria used by the judges. Next slide, please. So this year, again, as I mentioned, we had the most award submittals ever. Variety, really across a range of solutions. Innovation really is happening within our industry. You can visit our website, districtenergy.org, and you can find all the submittals for 2022, the winning submittals. We'd also would urge participants to consider submitting for 2023. The application process is now open. So let me introduce the three presentations we'll hear today. We're going to start with two honorable mention winners. The first from Emicool, our colleagues in Dubai. It's a chilled water network leak detection project. The presenters are Jad Hunaini, who's Assistant Energy Manager, and Ahmed Shehata is Assistant Digital Control Technology Manager. Emicool will be followed by Enwave Energy Corporation. Cameron Leach, who's the Senior Manager of Solutions and Innovations, will be talking about a very interesting project they've done applying heat pumps at a district energy scale, the advantages and outcomes there. Very interesting, I think, with a lot of opportunity. And let me backtrack just a slight amount. The amount of district cooling infrastructure that's being deployed across really the Middle East, really globally, I think the technology that Emicool is demonstrating will be of great value to our industry and certainly our members. And then finally, the winner for 2022 is Dalhousie University and FVB Energy. The presentation will be about utilizing an organic Rankine cycle technology to improve the overall campus district energy system efficiencies at Dalhousie. So it's a very interesting modernization upgrade. The presenters include Kevin Craig, who's chief engineer, and Daryl Boutelier. I think I got that right, Daryl. Boutelier, director of operations at Dalhousie University, and then Michael Conti, who's an engineering manager based in Toronto with FVB Energy. So that's our sequence for the day or morning, and we're going to start first with Emicool. Let me turn it over to Jad and Ahmed. Please take it away.
Hi, Rob. Thanks a lot for the introduction, and we would like to thank the IDEA for giving us the opportunity. We've been always striving for innovation at Emicool. So for this year, we will be presenting the chilled water network leak detection system project. Next slide, please, Tanya. So just to give you a quick introduction about Emicool, Emicool is a leading district cooling service provider at the UAE. It was established in 2003 in the Emirate of Dubai. Recently, within this year, Dubai Investments, the sole owner at that time, sold 50% of its stake to Actis. A quick show of our energy excellence journey. Since 2012, Emicool started investing a lot into energy itself, from water and energy and electricity. And mainly in 2019, we launched our energy efficiency retrofit program, which is still ongoing up till now. And in 2020, we launched our command and control center. 2021, we started the implementation or the actual implementation of our leak detection system. And within this year, we started and launched our energy management information system. Next slide, please, Tanya. So just to give you some facts on the water itself, since this presentation is focused on the leak detection. As per the Global Water Intelligence reports, the leakage rates in distribution systems worldwide on average is around 20%. Focusing on UAE itself, this drops down into 10% of water leaks as per Dubai Electricity and Water Authority's reports. So if we look at Emicool itself, as per our latest data, on average for the past 4 years, the water that we have been losing through leaks in our chilled water network is almost around 1.2%, which is not quite high, but if we look at the volume of water, it's quite effective. In 2019, we were at around 14 million imperial gallons of water, and we worked so hard for the past 4 years to drop it almost by 50% to 6.4 million. So this percentage has dropped drastically from 2.2% up to 0.9% through the past 4 years. Next slide, please. So how did we come up with the leak detection initiative? So in 2018, when we were going through our energy strategy for a 5-year plan strategy, we set a goal towards reducing or controlling more our water leakages, as we were losing a lot of water. So we defined the goal in 2018, and we noticed that we were continuously using the same conventional methodologies of controlling leaks, which were more or less non-effective at that time. So we set our goal in 2018, and then in 2019 onwards, we started seeking for a strategic technology partner, and we set some framework for establishing the right partner. 2019, and we started this research and development with our partner, and our first pilot project and trial started in 2020 in our DIP chilled water network. So in 2021, beginning of 2021, we have moved on or transitioned to the second phase of the project, which is another chilled water network across our DIP. And we have set 3 additional phases to be implemented for this system for the coming years in 2022 and 2023 till we implement it across all of our chilled water networks. I'll move on to the next slide, and I'll let my colleague, Mr. Ahmed, to present more about this technology.
Thank you, Jed. Hello, everyone. I will explain about the technology, and what we have exactly for the leak detection system. Actually, Emicool have a fiber optic cable network which run along of the chilled water piping network, which mainly used for communication purpose. We use it for remotely reading for the bitumeter and cooling the cooling meter from the customer end, which required for billing, and also we use it for remote monitoring and control for the energy transfer station at each building from the command and control center. But now we have an additional purpose for the fiber optic cable, in addition to the remote control and monitor, and for the remote reading of the bitumeters. We use the fiber optic cable for leak detection as a leak detection sensor to detect and determine the location of the leak along of the chilled water pipe. Okay. I will explain to you how the DTS system is working. DTS, it stands for distributed temperature sensor. We utilize the fiber optic cable with high accuracy to determine this distributed temperature sensor is able to sense the temperature over a long range with accuracy of plus or minus 1 degree Celsius. This system is composed of 2 parts. With the first part is the device that sends the light. You can see here in the down graph. The first part is a device that sends the light signal into the fiber optic cable and receives the reflection generated by light scattering as light travels through the fiber optic cable. Okay. The second part of the system is, of course, the fiber optic cable itself. The fiber optic cable is consisted of 2 media, core and claddings, and because of the microscopic changes of the media reflection index, when the light travel, the reflections happen at every point of the fiber optic cable, and this reflection is travel back in the opposite direction of the original light. This reflection are received by a highly sensitive device, this DTS device, and once we receive this light, you can see this graph in the right-hand side. If we draw the frequency spectrum of the reflected light or signal, then it would look like this graph. This graph shows the reflected light wave will have the majority of the power concentrated around the frequency that transmitted in the first place. However, we will see a certain peaks at different frequency as well. The right side of the spectrum of this graph is known as strokes, and the left side is known as anti-strokes. Okay, in the stroke in the both side you will find two peaks. In the its name Berlin and Raymond peaks. Okay, in the Berlin and Raymond peaks we can determine the temperature by in the Raymond peak we can determine by the amplitude of the signal, and in the Berlin we can determine the temperature by the frequency of the peak. Okay, we use this technology. We use this technology to determine exactly where is the leak where is the location of this leak. Can we go for the next slide, please? Okay, you can see here the thermal map, the real-time GIS thermal map for the fiber optic cable along of our chilled water network. Wherever any leak happen, we can see the difference of the color, where is the exact location of the leak in this thermal map. Currently, actually, we cover around 174 kilometers of a chilled water pipe, and by 2023, we will add around 25 kilometers of a chilled water pipe to cover under this leak detection system. Jet, you can continue.
Thank you. Next slide, please, Tanya. So just to give you a quick overview of the system's benefits, we can categorize it into both into three different things: environmental and operational benefits, as well as economical benefits. So how the leak detection system has helped us, it helped in the reduction of natural resources utilized, like water, for example. We're controlling the water. This is the main intent. And protection of environment from chemicals. The chilled water network usually has some chemicals that are required, like nitrite and some other chemicals that might be not healthy for the environment or harmful for the environment. Third thing is reduction of excavation. So one good benefit, how do we reduce the excavation, is, as Mr. Ahmed has just mentioned, when we locate the area rather than rather than excavating in the wrong area or wrong location, or wait till the water reaches the surface level so that we can allocate the water. This helps us a lot in allocating the right place for the excavation. Similarly, from an operational improvement perspective, when we're reducing the chilled water leakages, we can as well improve the transmission losses across the full network, improve the energy management as well. So all of those points translate into economical benefits, where we have seen some reduction in the cost of water that is being lost, as well as reduction in the cost of chemicals that we are losing through those leakages, reduction in the cost of excavations, as well as the leak repairs, in addition to both the transmission losses and the plant electricity cost from an operational perspective. So next slide. This is all that we have. We thank you a lot for having us.
Well done, Jad and Ahmed. Thank you very much. We'll certainly be coming back to you with questions at the conclusion. And clearly, you know, water is a very precious resource, not only in the UAE, but globally. So thank you for sharing that information. We'll come back to you shortly with some questions. So on to our next presentation, Tanya. My pleasure to introduce Cameron Leach from Enwave in Toronto. Cameron, please take it away.
Thanks, Rob. Good morning or good afternoon to all, and thanks for the opportunity to present the topic of district heat recovery to you today. My name is Cameron Leach, as Rob said. I'm a senior manager with Enwave, and I was the technical lead on 3 of the district heat recovery plants that we're looking at today. Decarbonization and the role that district energy can play in the energy transition is a familiar topic to us all. District energy is positioned to be a leader in addressing climate change, but there are regulatory and commercial forces at play that will accelerate adoption. From a regulatory perspective, building codes and energy standards are mandating reduced emission designs. To remain relevant, district energy suppliers need to have products that meet the requirements of developers and customers. From a market perspective, carbon pricing and customer expectations are pushing district energy operators toward low carbon system development. In Canada, carbon pricing that increases to $170 per ton levels by 2030 is helping to make electricity-based systems competitive, and significant demand from developers, landlords, and their tenants for low carbon heating is forcing DE to innovate and provide low carbon solutions to serve their existing and growing customer base. Obviously, transitioning to low carbon heating networks, which generally means electrifying heating, is a priority, but it's not without its challenges. 2 primary considerations are utility costs and electrical grid constraints. Although the graph shown here is a representative forecast for utility costs in Ontario, fossil fuel-based energy prices are commonly lower than electricity on a dollar per unit energy basis. In Ontario, electricity is currently 4 to 5 times the base cost of natural gas, using a blended cost for electrical demand and consumption. With the introduction of increased carbon pricing, the gap is closed substantially, but it appears likely that natural gas will remain at a lower cost well into the future. In addition, having the ambition to decarbonize by switching from fossil fuels to electricity doesn't mean that the electrical utility will be able to accommodate. Most electrical grids are constrained, or they would become significantly constrained through the rapid electrification of heating systems. Next slide, please. Based on the foregoing slide, it becomes obvious that a one-to-one replacement of existing fossil fuel-based boilers to electrical boilers isn't going to solve the most challenging problems. In many municipalities, the market cost for electricity may be considerably higher than their fossil fuel equivalents. And except in those locations with abundant and low-cost electricity, it's unlikely that electrical utilities will be able to accommodate the significant demand increase imposed by a transition to electric boilers. Heat pumps help overcome these issues by the multiplying effect of energy input to energy output if one has an available and adequate heat source. This multiplying effect is represented in the unit coefficient of performance, or COP, and it directly and proportionally improves production costs, reduces GHGs, and more fully leverages the electrical capacity from a potentially constrained grid. This chart shows a representative forecast of cost per unit energy produced over time in the Ontario market. The 2 blue lines are the production cost for a heat pump plant with a COP of 2.8. Class B is Ontario's flat but higher electricity rate. Class A is an industrial rate that charges customers based on their contribution to grid peaks. And the curve shown here assumes the heat pump plant avoids those peak charges. The bottom red line is the base production cost for a 90% efficient gas boiler without carbon pricing. And the dashed red line shows the total production cost for the same boiler, including carbon pricing. The main takeaways are that even now, a heat pump plant on a Class A rate structure has the potential to produce heating at lower costs than the natural gas alternative. And within the next 3 to 4 years, even the flat Class B rate structure will become competitive. Next slide, please. So that brings us to the implementation of heat pumps with district energy systems. One application for district connected heat pumps exists for distributed local plants. Take, for example, an existing steam customer who is looking to decarbonize, who has access to district chilled water, but they don't have access to a nearby district heating water system. That customer's cooling and heating profile over the year may look like the graph on the left. In this case, the customer could consider building a standalone heat pump plant to serve their heating profile. But generally, the heat pump plant would be sized for the peak coincident cooling load available. In this application, while the total heating required for the building is represented by the area under the red curve, the standalone heat pumps are limited to producing the area shown in green. If instead that customer can access the heat source created by other district energy customers with year-round cooling loads, a local heat pump plant can be sized for greater than the coincident heating and cooling peak of the building, allowing the customer to tune the plant size to meet their carbon targets, up to and including their entire heating load, the area under the red curve. The graph on the right represents Enwave Toronto's cooling load over a typical year, and it reflects a minimum heat source for district heat recovery of approximately 10,000 tons. Next slide, please. The prior slide was focused on district heat recovery plants implemented at customer sites and designed to serve only the customer's heating load. Another implementation involves the construction of centralized district heat recovery plants. This is the configuration of the 3 district heat recovery plants discussed in this presentation. This arrangement is represented in the simplified schematic on the left. Heating water returned from our customers at around 120 F is routed first through the heat recovery chillers before being topped up by downstream high-grade heat sources. This configuration has several merits, but the 2 primary benefits are simplified operation, in that the heat recovery plant only has to maintain leaving chilled water temperatures, and high utilization. This high utilization results in significant impact with relatively modest installed capacity. The graph on the right shows a representative load duration curve for a district heating water system, with demand shown on the red curve and the operation of a district connected heat pump in green. The area under the green curve represents the utilization of the heat pump, and the difference between the red curve and the green curve represents the higher grade heat source energy. In this example, the heat pump makes up somewhere around 25% of the installed heating capacity, but more than 60% of the annual heating production, which has a significant impact on carbon emissions relative to business as usual. Next slide, please. As noted previously, the 3 district heat recovery plants that are the focus of this presentation have been configured as base load heating assets. DHR Plant 1 is nominally 1,350 tons, composed of 3 high lift centrifugal chillers. Its design basis was to provide 135 F leaving the condenser, while producing 39 F leaving the evaporator. DHR Plant 2 is a single nominal 200-ton screw compressor chiller. It can produce 140 F heating water coincident with 40 F chilled water. And DHR Plant 3 hasn't been constructed yet, but will feature 2 1,800-ton compound centrifugal chillers capable of producing 170 F coincident with 39 F chilled water. It will be online for the winter of 2024. As we can see, the efficiency of the individual plants varies depending on compressor technology and lift conditions. But one common feature is significant carbon reductions relative to a conventional gas-fired boiler plant, even with modest installed heat pump capacities. For example, DHR Plant 1 has heat recovery chillers equal to approximately 10% of the installed plant capacity, but produces almost 30% of the annual heating energy. DHR Plant 3 will have heat recovery chillers totaling less than 30% of the total installed capacity of the plant, but produce up to 75% of the annual heating energy. These high utilization factors are reflected in the carbon savings noted. Next slide, please. Through the design, construction, and operation of DHR Plants 1 and 2, there were lessons learned that informed our approach for DHR Plant 3. As it relates to the heat pump selection, our primary focus was to maximize utilization. Traditionally, heat pumps have been able to produce temperatures that are slightly above those in a typical cooling tower loop. By increasing this temperature, we can serve year-round domestic water heating loads and encourage uptake by existing buildings that may have legacy systems with higher temperature requirements. Secondly, the high-lift centrifugal chillers at DHR Plant 1 have limited turndown. And so at especially low loads, there may not be adequate district heating load to operate these units. It was important to have higher turndown capabilities at DHR Plant 3 to extend their operating range. As it relates to controls, the operation of a base load district heat recovery plant is simplified, in that control of the leaving evaporator temperature is the focus, and we simply get what we get in terms of temperature from the condenser. At DHR Plant 3, we're incorporating the ability to also adjust the leaving temperatures from the condenser in order to maximize utilization year-round. Lastly, as it relates to commissioning, we learned that it's important to be able to replicate district conditions, especially with relatively new heating water districts, as was the case for DHR Plant 1, where there may not be significant district load and customers may not yet be properly tuned. One either has to develop a detailed plan to simulate district conditions or accept that commissioning of all aspects may not be complete until the district has matured. DHR Plant 3 will be commissioned as part of a mature heating water district, and so we anticipate fewer challenges to that project. Next slide, please. And with that, our presentation on district heat recovery plants in Toronto is complete. Thanks to the IDEA and the attendees for providing the opportunity to speak with you today.
Thank you very much, Cameron. Very interesting. Obviously, this demonstrates the advantages of aggregation and scale that district energy provides to the community. So I really appreciate it. We'll be coming back to you with questions to follow. So thank you again to our colleagues at Enwave and Cameron. Let me now invite our final presentation from Dalhousie and FVB, Kevin and Daryl of Dalhousie and Michael of FVB, please take it away.
Thanks so much, Rob. Really appreciate being here today and joining everyone. Also want to thank the IDEA for honoring us with this award. Also want to congratulate our friends at Emicool and Enwave on their honorable mention. Really enjoyed their presentations. So our presentation today is about utilizing organic Rankine cycle technology to improve campus district energy system efficiencies. Next slide, please. And I'm going to kick things off with a bit of a project background and overview, and then I'm going to hand it over to Michael Conte to talk about our technical solution and campus conversion to hot water. And finally, our chief engineer, Kevin Craig, will discuss operational considerations and project summary. Next slide. And I'll go to the next slide, please, after that too. So for those of you who are not familiar with Dalhousie University, we're located in Halifax, Nova Scotia, our main campus. But we do have a beautiful satellite campus, our agricultural campus, which is located about an hour away from Halifax in Bible Hill. The campus has a fully functioning farm and is pretty much maintained to a level of a botanical garden. It has probably 55 buildings, 800,000 square feet of buildings, and I think our enrollment is somewhere around 1,000 students. Before we completed this project, the campus heating plant produced about 8 megawatts of thermal energy, and our biomass boiler and backup oil boilers at peak produced about 27,500 pounds per hour of steam. And in a year, we consumed about 8,000 metric tons of biomass. You can see the picture of our old biomass boiler to the side there. It was 30 years old, and unfortunately in 2014, we found internal fractures and cracks inside the boiler. We had to shut it down for a few months to make repairs, but also we had to make negotiations and concessions with the Department of Labor to allow us to restart the boiler. And we had to put certain parameters and considerations in place to run that boiler. But essentially, we knew that we'd have to replace it. Also, in addition to the old boiler, that was basically in a failure state, we had a 40-year-old steam distribution and condensate distribution that needed major renewal. Next slide. So when universities know they have to spend a lot of money on infrastructure, we try to get the best bang for our buck. So we set lots of project goals and try to incorporate all sorts of different goals into that project. For this one, we obviously wanted to align with our sustainability goals for the campus for reducing carbon and in line with our campus energy master plan. Universities are renowned for having large maintenance backlogs, and we're no different. So we want to address some of our facilities renewal costs by replacing some of our existing end-of-life equipment. Obviously, burning biomass, you have to worry about particulate and air quality. So we wanted to incorporate an ESP, electrostatic precipitator, and cyclone filters, which the previous plant did not have. Also, when it comes to biomass, there's a lot of focus on biomass and how it's procured, I guess, from forestry practices. So we want to focus on local biomass from sustainable sources such as sawmill residue, bark, and sawdust. And as a university, anytime we do a project, we like to incorporate research and teaching into that project. So we wanted to put in dual fuel bins so we could separate to different feedstocks such as willow and agricultural grasses and those types of things, so that students and others, researchers, could actually research some of those products. And as always, anytime we do a project, we like to seek grants, incentives, or revenue possibilities to help fund the project. Next slide, please. When we started planning this project, we had a real boost at the start of the project. We were very fortunate that the boiler failed when it did. The province of Nova Scotia at the time had a program in place, a community feed-in tariff program for renewable energy electricity generation projects from either biomass, wind, or solar. So we decided to submit an application for this tariff for a 1 megawatt biomass fired cogen plant, and we were successful. And the big benefit of this program for 20 years with your approval is that whatever electricity that you did generate, you would receive $175 per megawatt from the utility for that power by supplying it to the grid. So this was a really big boost to our project. So at that time, we knew that we had a lot of different options. We wanted to make sure we had an expert working with us. So we hired FVB Energy, who we worked with a few times before on some other projects, and we started to plan our project. Since our project was a biomass confit project, we obviously knew that we needed to have some sort of a new biomass combustor. We obviously needed air quality controls with an ESP, and we wanted to have dual fuel bins for looking at different types of biomass. We also wanted to get rid of that old steam condensate system, so we wanted to do a complete campus conversion from steam to hot water. So really the only big decision that we had to make was how we were going to generate our electricity. And when we started looking at the options of using the traditional methods of, buying a biomass boiler and producing high pressure steam, and then, producing electricity from, back pressure or extracting that high pressure, we really didn't like that idea. So we wanted to look at something more innovative. And that's when FVB brought this idea to us about organic Rankine cycle turbines. And I'm an engineer. I'd heard of Rankine cycle process before, but I hadn't heard of an organic Rankine cycle turbine. But once we started looking at it, it really did make the most sense for our ComFit project and for our sustainability goals, and as well as our operations. So in the end, we developed a project that was around $26 million. We got approval from our board. The only caveat was that with the ComFit, we had a timeline on when we had to produce that megawatt of electricity. And by the time we had project approval, we had less than 24 months to design and build the plant. So at this point, I'm going to hand it over to Mike Conte to explain the technical solution and our plant conversion. Michael, over to you.
Okay, thanks, Daryl. And I just wanted to echo, Daryl and some of the other panelists that, we really do appreciate the IDA providing this forum and really allowing, people in our industry to celebrate innovation. And thank you to that, and definitely thank you to the other finalists. Next slide, please. So before I get into the technical solution, I just wanted to introduce myself. So as Daryl mentioned, I'm Michael Conte with FVB Energy. I'm engineering manager of our Toronto office. And for this specific project, I was responsible for all the project management as well as complete design oversight. So it was a good chunk of my life for a few years there. Next slide, please. So just to talk a little bit about the biomass system that we did have to replace, it's a 5.4 megawatt thermal combustion system with an attached thermal oil heater. So we went through a competitive RFP process, and we decided to align with Wellens FEI to supply this system. So they were the supplier of the combustor, the thermal oil heater, and the fuel handling equipment that you can see in the photo on the right. It's a step grade combustor. And it's a similar in technology to the boiler that was there, but it is a more modernized version of it. And you'll see there on the right-hand side that, as Daryl mentioned, it was important for the university to have the ability to do some research with this system. So we managed to incorporate these dual fuel bins into the biomass fuel feed. And that has allowed them throughout the years to play with different fuels, short rotation crops such as willows, tree barks, things like that, in addition to their more common hog fuel type fuels that they're delivering. So that's the image there of the dual fuel bins on the right. Next slide, please. So the biomass heater, so I mentioned thermal oil heater. So the biomass, as it's combusted, heats up a closed loop thermal oil system to a high temperature. And that thermal oil is circulated to our organic Rankine cycle turbine. So that turbine takes the high temperature oil and converts it into electricity via the organic Rankine cycle process and the connected generator. And then all the cooling that happens with the turbine is heat that is rejected into our district heating system. So when you combine the electrical and thermal efficiencies, it's a very high efficiency unit with 98% of the energy being recovered by either electricity or useful thermal energy. And you'll see there that through that conflict contract, which is, you're able to run your electricity 365, 24/7, 365. So outside of a little bit of downtime for maintenance, we're able to produce about 8,000 megawatt hours of electricity. Now that gets exported to the grid through the contract, but it equates to about 75% of the total campus electrical use on that campus. And again, all that electricity comes from sustainable biomass. Next slide, please. So as part of this project too, as Daryl mentioned, these projects are sensitive to capital, and we did have, we couldn't rely completely on our new biomass system. We did need to have redundancy. I mean, after all, this is a district heating network supplying multiple buildings on campus. So utilizing existing assets was extremely important. And we worked with Cleaver Brooks. They had a boiler that was about 10 years old at the time. It was their newest boiler. And we were able to take that boiler, which was generating steam with fuel oil, and convert it over to generating hot water. So this was actually a very important part of the project, as it allowed us to keep that budget down and allowed us to keep the project in the positive. And it's worked out extremely well. So this boiler provides backup thermal when the biomass boiler can't meet the loads, and also during those times when Dalhousie needs to service the biomass system. Next slide, please. As Daryl mentioned earlier, air quality was important, very important to the university, especially with a biomass system like this. Per the COMFIT requirements, we were required to meet a threshold of 135 milligrams per meter cubed. That was the rule with the biomass-based COMFIT system. But Dalhousie did elect to go above and beyond that and push and mandate the installation of this electrostatic precipitator for further particulate control. So with that, we were able to get down to 35 milligrams per meter cubed. And as you can see in the picture there aside, I don't know why I remember this, but we tried to paint it a nice cocoa brown color, I think was the color they used, to try to minimize the aesthetic of the ESP on the campus. And I think it turned out quite well. It blends in a little bit with the plant there. Next slide, please. So campus conversion was discussed, and Daryl mentioned it earlier, and this was a critical, I would say this was a bit of the horse driving the cart here. I mean, without the ability to convert that campus over to hot water, we really never would have been able to utilize the ORC technology like we did and meet the efficiencies that we did. So this was a critical part of the project. And as Daryl mentioned there, we had a little under 2 years to execute this work. So as you can imagine, we have a fully occupied functioning campus, and we had 2 years to do a full conversion. Next slide, please. So to highlight some of the things we had to do with the campus, we had to run all new hot water piping. There was steam infrastructure in the ground that was over 40 years old. So we elected to go with EN 253 pre-insulated heating pipes. And all in all, we ran about 1,300 trench meters over the course of 2 summers. The image there shows a photo connecting one of the buildings campus. You can see that nice red soil that they have out in the Maritimes. Next slide, please. In addition to this, we had to install 16 new hot water energy transfer stations. So the campus was set up where most of the buildings did take hot steam and convert it to hot water at the entrance to the building. So a number of buildings, it was just a matter of swapping heat exchangers. But there were buildings that did take steam right to the terminal units. That included anything from humidifiers to sterilizers. The kitchen even took steam right to a big wok that they used in preparing meals. So we had to replace and convert all those systems over to accept hot water. Next slide, please. In addition to the boiler, which I mentioned earlier that we're able to repurpose, we actually were able to utilize some dual steam lines that they had installed. So lucky for us, I guess, when the engineer put this piping, these tunnels in the ground in 1968, they decided to go with fully redundant steam and condensate lines for a portion of the system. So working with the contractor on the project, we did full inspection of these tunnels and realized that the 2 steam pipes were actually in fairly decent shape. So we had to, design out the replacement of some compensators. We had to upgrade some of the steel supports, but we were able to reuse a good portion of these steam lines, which is actually one of the main arteries that connects the north and south campuses. So again, this really helped with controlling project costs and utilizing the existing asset that otherwise would have just been a sunk cost on the project. Next slide, please. And this part is probably the most important. I think this is something that I think it can't be understated here. I mean, we're all district energy professionals. I assume most of us on this call, and our business is supplying thermal energy. But really, a campus, a respected university like Dalhousie, they're in the business of providing education and research and development for their students. So even if we designed and implemented the greatest district energy thermal system, project would not have been a success if we interrupted the campus and what they were doing. And this campus had some critical research. This is where the aquaculture at Dalhousie, Daryl mentioned they've got an active farm, so they have a lot of wildlife. They have PhD students with 8+ years of continuous research that they've been working on that are dependent on those thermal systems. So one of the proudest things, I think, looking back at this project, is that we implemented a full campus conversion, a biomass system replacement, and there were 0 interruptions to that core campus. No students lost any research. Most students probably wouldn't have even known what was happening. It happened in the background. So this was a very important aspect of the project, and one that maybe doesn't get highlighted as much in this forum, but I think it was one of the proudest accomplishments on the project. Next slide, please. So with that, I'm gonna hand the presentation over to Kevin Craig, the Chief Plant Operator, and he was very patient during the course of this project and having to maintain the system throughout. So Kevin, over to you.
Okay, thank you, Michael, and appreciate the opportunity to be here, and of course to see the other innovations and such. And I think overall everything went quite well with this project. Next slide, please. The York system, I guess, is almost a bit of a standalone system, at least operationally we consider it that way, and it was the units that connected together, and has been quite little maintenance required, other than, I guess, during commissioning. There was some hiccups there, as can be, some dirt in the strainers and stuff like that. The Welland system, which I'd say is another integral part of the whole system, which often gets called a boiler because it is very similar to a boiler, other than it doesn't have drums, steam drum or water drums. In this case, it's full of thermal oil rather than water, of course. And itself, the actual unit, there's not much issue. We had a little refractory trouble here and there, but nothing too serious. And a big part of it is the fuel itself, which is at a supplier in today, giving us a couple options with our fuel from the sawmills, because of course that can vary as per what the sawmill's producing and doing, and what they're selling, and market prices and all that stuff. And it's a factor that helps us towards making our maximum power, such as moisture is a critical part of it. As moisture, and we did have initially in last winter we did quite well, but the previous winter, I guess you'd say 2020, we had a lot of frozen chunks and severe damage to our conveyor, but we learned some lessons from that and put in some sensors, and along with working with our biofuel suppliers, I think we've done well to get around and improve the fuel and the problems. We did get a chain here a couple of weeks ago, which none of the suppliers seem to know for sure where it came from, but those sort of things happen when you're talking massive buckets on payloaders. Next slide, please. There, speaking of our fuel, is our dual fuel bin, which is all one building, but you can see the dividing wall in the middle that allows, and the system as per design can run independently. You could have one type of fuel on the left side and a different type on the other, partly for mixing purposes, or as Daryl pointed out, research and that sort of thing. Willow tree and any other future potential biofuels. Knock on wood, so to speak, we're lucky right now. We've got 2 local sawmills that are giving us all, we're burning pretty close to 100% mill waste. So that's, I guess, is being sustainable and not cutting, having any trees cut specifically for us. That's a good thing. Next slide, please. It's been a couple of years since I've been in the details of the specifications and all this, but I mean, to in-depth consideration, but there's, as it says, 11,000 saved in energy. A big part of that is what Michael pointed out, was the new mechanical rooms, because you're basically comparing an old steam system with some steam traps that are needing some PM versus a new hot water system. So even a new steam system to a new hot water system, certainly the hot water better suited here, towards the energy requirements. And but it was a much increase in energy savings, old steam versus new hot water. The electrical generation, as Michael pointed out, was 75%. We often get questions. People make the assumption, which is normal, that the power is for the campus. Well, indirectly, it all goes to the grid, because we get a premium rate as part of the ComFit system. And that premium rate is more than what we pay for it. So we sell, as per our contracted agreement, every kilowatt, and then which is equal to 75%. The new system is certainly a fairly up-to-date system, especially compared to our old biofuel system, which was smaller and didn't have utilization of some of the newer considerations for burning and emissions and that sort of thing, such as ESP and all that. Our ash has been one of our challenges, so to speak, but we do have a agricultural license and can be used on farms is to sweeten the soil. Our challenge mainly with the ash is making sure it's cool by wetting it down and that sort of thing. But certainly there's good interest from local farms to use it. The price of lime has gone high, so that's even makes it more high. Next slide, please. There's some numbers, I guess, of indicating the performance and how, I guess, giving credit to, of course, design and operations and operators who run the system, including myself as managing operations of this plant. We've exceeded most cases the design by a little bit in fine tuning the system to get a little over 1 megawatt. Our goal is often 10% to 20% over the 1 megawatt. But we have some downtime, so that's, some unscheduled breakdowns and different things. So if we can exceed that 1 megawatt, then that gives us a little bit of reserve in our total energy production. The costs, as seen there, I guess are pretty close to what was estimated. Energy costs are rising quite significantly. Knock on wood, our biofuel is relatively stable as per our last contract about 1 year ago. Power generation, of course, that's also increased as I mentioned, we try to, our goal is to be slightly over. And our contract for our fuel is locked in for 3 years. So that's easier done, I think, with biofuel and sawmills, that sort of thing. Next slide, please. Certainly there was a high level. I was quite impressed with the high level of communications and all things. If there was issues with the project and all that, or concerns, not so much issues, but concerns and questions. We had great communication, I think, on all levels. As kind of mentioned with the operators trying to have a bit of a goal of going just above that 1 megawatt, that's as part of it there. They contribute towards certainly the long term of the plant and the maintenance and PM and that sort. Yeah, the 10.2 renewal requirements addressed in the scope. That's, I guess, mechanic rooms. The reliability has been good. We had a Fiona, whether you heard of it or not. It was a big storm here, a hurricane that moved up the coast, of course, and I guess certainly the eastern states would have heard of it. And we were affected by, I think, about 11 days of being off because of it. Because if the grid is unstable or the grid is off, the power grid, we can't put power onto it. That's part of our the design. We certainly don't want to be putting power on the grid when the grid is shut down, and also if the grid is unstable, we also have trouble synchronization. So during severe weather events, the grid can become unstable, as say maybe 5,000 customers are shut off nearby or something, or have an outage, I should say, rather than shut off. And the Terboden, that was, I think, touched upon. That's quite a reliable system, and knock on wood, and it's been quite a standalone system that we do monitor and have more control and synchronization issues on rare occasion than anything else. Next slide, please. And I wish to thank you on behalf of Dalhousie and FVB and everybody involved. We even had a control company in earlier. Certainly they were even a part of it. So thank you very much. And to IDEA, of course, of putting on this. Very good.
Thank you, Kevin. Thank you. And I'd like to invite all of our panelists to return, but, just a notion on the Dalhousie FVB project. It sounded like, sort of building the plane as you were flying in a way with a 24-month project cycle. That's that in itself is quite a challenge to overcome. So now, I'd like to kind of pose a couple of questions to all the panelists. And let me start back at the beginning with Emicool. So one of the questions, Jad and Ahmed, what type of piping are you using in your network? And secondly, can you estimate the total volume of water that's circulating? Jad.
So thank you, Rob, for those questions. So mainly we have different type of chilled water pipe. We have pre-insulated mild steel. There's GRP, HDPE, and for the volume of water, it's somewhere more than 150,000 cubic meter because across all the networks, because we are supplying, we have a connected load of somewhere around 300,000 tons of refrigeration.
Wow. 300,000 ton. That's significant. That's almost the whole industry here in North America. Just to stay on that for a moment, like leak detection, obviously in UAE, water is very precious, right? And so, any gallon is of value. And I know in some locations they've used sort of, food coloring, right, for water. So if there's a sort of a, pink water, then it's chilled water. But I would guess that in the UAE that, the challenge of district cooling versus steam is that the temperature differential, like I would think cold water is going to dissipate quickly, right? In the underground of Dubai. So having a fiber optic sort of tell seems to be very valuable. And you've cut your water leakage by over 50% in that period. What percentage of your network is currently covered? And do you think you'll get to nearly 100% sometime soon? Is that the game plan?
So definitely the game plan is to reach 100%. This was our initial goal, and this is how we initiatives are always driven. Let's say I'd say we have covered somewhere around 50% of our network so far. We've covered the majority of our DIP area. There are some other areas, but DIP is one of the biggest. So past 2-3 years, we've been handling this area mainly.
Very good. Well, thank you. And obviously, I think the technology has tremendous potential across our membership. And, so thank you. I'll come back to you with a couple more. If I could now jump to Cameron at Enwave. So Cameron, your presentation really does, I think, demonstrate that, the aggregation, the scale of district energy, being able to sort of, utilize a heat pump in this way. You're not dependent on the heating cooling needs of an individual building, right? You're basically, utilizing the full output. So my question though is, and this was not apparent to me. You mentioned that the price of electricity on a delivered basis is about 4 times the cost currently of like natural gas, right? Now, does that mean that having a COP in the range of 4 is really required to kind of get to a balance point economically? Is that something we should be thinking about?
Yeah, thanks, Rob. I think that's exactly right. If you were talking purely on dollar per unit energy purchased from the utility, if you were running a natural gas boiler, it would be 4 or 5 times less expensive than an equivalently sized electric boiler. Now, of course, in Ontario, at least, we have our electrical utilities charged based on demand and consumption. So if you make the mistake of turning the electric boiler on the last day of the month, you're probably going to see much higher relative pricing. But, making some assumptions around utilization and demand and consumption, it's in that range. And so you're exactly right that you need to get to a point where the COP of the plant is going to overcome that shortfall on the cost of electricity.
And you also mentioned, Cameron, that with the first 2 installations, the first 2 projects, you didn't really have the native load yet, right? But with this 3rd iteration, it's being integrated into a more mature network, and therefore you kind of have a sense that it'll hit your design parameters sort of almost immediately. Am I right there?
Yep, yeah, that's completely correct. One of the challenges, and it was more the first plant, the DHR1 plant, where
Right.
the plant was constructed with the heat recovery chillers to serve a new heating water expansion.
Yes.
And so as the plant was coming online, so were customers, and a lot
I
of those
see.
customers were looking for construction heat, and maybe they hadn't commissioned their building side controls, so we weren't getting
Yeah.
return temperatures that we like, and the loads fluctuated quite a bit. So it was very challenging to try to commission relative to expected operation in the early
Yeah.
days.
Yes.
The second district heat recovery plant was there's a 3-office tower complex in Toronto, and the first 2 towers were existing and already being served on a heating water node by steam to hot water. And for the 3rd tower, the heat pump was incorporated, and so it's been able to perform as we expected. And in fact, we're getting more kilowatt hours out of it than we expected, because there is that resident load, so we can leverage the heat pump quite a bit.
Very good. That was one of the questions. We had a workshop last week in New York City, and one of the questions was sort of the lead lag on capital and customers, right? So with a new build, you really are dependent in some ways on the occupancy of the building, not, so we certainly construction heat, but and then you really do need the internally generated BTUs of people and computers, et cetera. So I can see where there's advantage to having both new build and existing buildings, to serve. Thanks, Cameron. I'm going to come back to you a bit because there's certainly more to cover there. Over to Dalhousie. As I mentioned, this is a very interesting project, and certainly the achievement of maintaining operation, supporting the sort of the research of the campus. Just a quick question of my own. In terms of the biomass supply, so really you're really like the circular economy, right? You're taking sawmill residue, making heat and power, and then sort of releasing ash for fertilizer, right? So it's like the whole continuum you represent. Do you have any concerns? Kevin, you mentioned that the residue, the sawmill supply seems to be both abundant and accurate. Like you've solved for the supply issue, and it would seem like with the economy maybe faltering a bit, do you have any concerns about maintaining the resource?
No, not really. We're quite confident. Our main supplier is Irving, which you may have heard of Irving, because he's certainly a big company in Eastern Canada. They have multiple sawmills around the Maritimes. The one we're dealing with is only 5 kilometers away. There's a couple other sawmills, one Leadwich. So, and Nova Scotia, I think, has certainly still a decent amount of forest left to, 4 of these lumber mills. So,
Yes.
No, we're pretty confident. I think Irving, even our last contract gave us reassurances of Irving's stability, and they actually just put a little upgrade in their local mill.
Very
So,
good.
yeah.
I was going to ask the question about, I thought it might have been Hurricane Ian, but it was Fiona that actually hit the Maritimes, and really I think was quite a significant storm. Do you envision perhaps in the future maybe any movement towards like an islanding protocol or a microgrid solution where if in fact the grid is impaired, you could maintain electric supply, or
Yes, for sure.
Okay.
Yeah, so Michael might even better answer that. But I know in the design it was considered, but I think there was a little bit of a challenge, so to speak, with Nova Scotia Power.
Yes.
I think in future they are considering it, and like I say, Michael may have a little more insider information towards that. Would you, Michael? Or
yeah, I mean, it was something that was considered, and something that the university wanted to incorporate if possible, but just per the terms of that contract with Comfit, it wasn't possible.
Right.
When that contract expires, I mean, that's certainly something. This generator could go behind the meter. It could be used for islanding. Lots of possibilities exist.
Right. Yeah. Sometimes you can't have your cake and eat it too, right? If you're going to be sort of privy to the benefits of a comp fit, then you've got to live under those conditions. So that's understandable. But perhaps now, having kind of experienced a significant storm, maybe there'll be some consideration or future opportunity. We'll stay tuned to that.
Sure.
So
Well,
back, yeah. Something else to say, Kevin?
One quick point there.
Yeah.
At least in the winter, we can still make heat with the system. So even though we're not
Yes.
making power. Yeah.
Yes. And that's obviously essential, as we would all expect. So a question back to Emicool, if we could. I'm going to sorry to be bouncing around so much, but so the question is, where approximately do you place the DTS to get the best location? Because obviously, locating the leak is really the key thing is managing the cost of the dig. It's not necessarily the pipe or the equipment, but it's getting it to the right location. Is there a locational suggestion? And the other part of the question is, what would be a typical cause of a leak? Is it corrosion, equipment breakdown, joints, etc.? You mentioned 3 different kind of characteristics of piping. Is it connectivity of the pipe, Jad or Ahmed?
Actually, we place the DTS device in the starting point of the fiber optic cable.
Yep.
The main location we have in the central command command and control center, and we have another DTS device in another geographical area. Actually, each area have a different zone covered by different cable. Okay.
I see.
And
Yep.
each cable have a dedicated channel. For accuracy of the system, we are doing like a mapping between the fiber optic lens and the pipe lens. Let's say we go for each valve chamber, we apply a heat on the fiber cable. So in the so we can determine exactly where is the location of this fiber cable and what it means for the pipe. We do this mapping. 1 kilometer of pipe, it's equal for me 1.5 kilometer of fiber cable. We do such mapping in the beginning, so we can determine each location of the fiber and what is mean for and what is the reflect for the pipe. Okay. In the other part of the question, what is the what is the main purpose of the leak? Actually, most of the leak it's coming from the pipe cracks from due to ground setting, due to bad compaction of the soil, or due to bad welding or life cycle of the welding in the joint or in the elbows and the fitting. These are the main causes of the leaks, actually.
Sure.
And also for the GRB pipe, if any, due to the change of the pressure or the during the time, it's have some crack. This is the main causes of the leaks that we have. Sometimes also of bad setting of the valve chamber, because the valve chamber it's made of concrete. If there is a bad setting of for the valve chamber in the joints, it make such a crack in the joint or the entry point of the valve chamber.
Sure. Well, with that volume of pipe network, it's certainly understandable that there will be, causation. So, in case you didn't know, we're at extra time here with our Q&A segment, and we'll keep this World Cup moving. I did mention Joe Brillhart, and Joe really was the catalyst behind this award. Question was, and I think it was answered in the slides, but what is the ORC technology that was deployed at Dalhousie, and what percentage of the electricity? So the question is regarding the OSC, with electrical efficiency being 19%, what is being done with the remaining 81? And I think it was answered on the slide, but perhaps to either Michael or Kevin or Daryl.
I can probably field this one. So by the technology, I mean, the supplier was Turboden, a supplier out of Italy. If that was the question in terms of the technology, I mean, the technology was organic Rankine cycle turbine. It was a split casing turbine. Yeah, the electrical efficiency was 19%. The other 81% it goes to their hot water network.
Right.
So, and then if the hot water network doesn't have a need for it, then it gets rejected as to the radiators or the cooling towers.
Right. Right. Very
So
good.
the sink is actually is the district heating system, and then the backup sink is dry coolers.
Sure. Very good. Thank you. And then question about the pipe selection. What was the reason for using EN 253?
Yeah, I think I saw a couple of questions that pertain to that. So I mean, at that time, the temperature was the big thing and the pressure. So we were having to supply hot water as high as the design was up to 115 Celsius. So HDP was not an option.
Yeah.
And the contractors in the Maritimes, we had experience with the EN 253 steel piping. So we had some competent contractors in the area that were trained and knew the pipe well. So that was another factor as to why we chose the EN 253 steel system. And I remember this was also 5-6 years ago when we were doing, concept design. And I know HDP, high temperature HDP technology has come a long ways actually in the last 6 years. So, but some of those things weren't actually even available back then.
Yes.
In terms of high temperature options. So
yeah, and clearly, caution and design, design conditions, you don't really want to see hot water flash steam and have a rupture that makes the news cycle, right, for days. So I think, that makes perfect sense, at least to me. So another question on the ORC, the working fluid and the system pressures. Do you have sort of a great deal of turn down, and does that affect the efficiency of the unit?
yes, I mean the ORC itself. I mean, luckily this is a base loaded unit. It's producing electricity, like I said, 24/7, 365. So it doesn't need to turn down.
Wow.
But it has a turn down of about, I think 10-to-1 is what they advertise. But I know that the efficiency on the electrical side really starts to drop off once you get below 40 to 30%. The efficiency starts to drop off.
Right.
But luckily, I mean, for us it was not a factor because we're running this unit. It's running full out. It's been running full out year round. So.
And it's sized for that, really. And you obviously have a significant heat sink, at least I would have guessed, most of the year. Thank you. So a question over to Enwave on the DHR. So I know that in downtown Toronto, the prime mover is a steam system, but are these DHRs, are they deployed in hot water networks, or are they where do they sort of fit in the architecture of the district heating network in downtown Toronto? Are these Cameron, sort of nearby nodes that are hot water, or are they sort of feeding to the steam network?
Yeah, thanks, Rob. You're right that our steam network has certainly been the major heating source up until the last 5 years or so. And within those last 5 years, we've developed two significant expansions. So we have a western expansion that is about 2.5 kilometers of new heating water and chilled water piping, and then an eastern expansion which involves some mining and tunneling and stuff that goes about the same distance along the waterfront in Toronto. And so the district heat recovery plants that are in operation and the one that we're going to have online in another couple of years are connected to those new heating water nodes.
Got it.
But that said, an opportunity that we're seeing a lot of interest in with our existing customers is the ability to transition them from steam to hot water without the expense of running heating water pipes a great distance. So our network of steam piping is large in Toronto.
Yes.
But like any other dense urban center, running infrastructure in the street is oftentimes the barrier to provide an economical option for a new customer if they're not within a stone's throw of existing piping.
Right.
And so we have lots of customers that are existing with steam and chilled water. And so where they have ambitions to decarbonize, it's a great fit to throw some heat pumps on the district chilled water loop and generate a local plant, or construct a local plant that serves their heating water needs.
Yes, and interestingly, all roads lead to Rome, right? So just last week, Carlisle Coutinho and Rajesh Dixit from JCI were on a panel together in New York and talking about the deployment of Johnson Controls, heat pumps in Toronto. So really pleased to see all the progress and the innovation that continues, really led by Enwave. Another question over to Emicool. Is the fiber optic placed between the pipes, below, above, internal? I'm assuming myself that the fiber network is adjacent to the pipe. Is that correct? The fiber optic network?
Yes, actually, the fiber optic cable, it's laid in between, it's above the pipe, in between the pipe, around 30 centimeter above the pipe. And because most of the area we have, the water table, it's very high. If any leak happen, the chilled water is mixing with the groundwater, and it surrounds the pipe around it's around the fiber cable.
Yes.
And cool it down, so it reflects direct to our system. And also there is another point, in the summer in Dubai, the soil temperature it reached maybe 60 degree, and our chilled water it's 4 degree. Once any leak happens, there is a significant difference in the temperature, which can show immediately in the system. And also this DTS system, it's not it's not running once. No, we run it once and continuous running and reading all the day.
Yes.
And it's comparing the previous reading with the new reading. It's working like this. I have a reading every 5 minutes. I have a reading of all the connected network. And imagine if I have 25 kilometer of network, I have 25,000 of sensing temperature point along of my network, and this 25,000 sensing point every 5 minutes I have new reading.
Interesting.
If any change happen within 5 minutes, I can detect. I will compare the previous reading with the new reading.
Does
Then
it alarm? Does it alarm you? Does it send a?
Yes, it push me it give alarm if let's say in the location X, it give me a location with the coordinates, with meters, and it give me what is the previous reading and what is the new reading. Even I can run it with over time. What is the heat change over time? If it's a certain time, I can check what is the change of water. Even I can, after we install it, even we start to know what is the timing for irrigation system in this area. Once they start the irrigation, we know there is this irrigation timing.
Yes.
Not our chilled water. We know in this area there is a landscaping, and this is start irrigation. We can detect. We know in this time they start irrigation, the irrigation system.
And so you can sort of determine whether sort of it's a failure, right? A sort of a rupture or a gradual sort of seepage, right? Those conditions. Thank you, Ahmed.
Yes, yes.
Let me go to Dalhousie now for a final question as we're sort of nearing the end of extra time. And I know some of you are eager to get to the World Cup match. It's not quite ready, but we'll be there before we know it. So to Dalhousie, so two things jumped off the page to me. One was the 24-month sort of project cycle. And then secondly, the building conversions. Was that how did the building conversions go? Was that sort of the more challenging aspect of the project? And have you completed all of the building stock is now transferred to the new hot water network over to Dalhousie FVB?
Daryl, do you want me to take this one, or?
Sure, go for it.
I think your first question there, Rob, so what was more challenging? I mean, it was certainly the building conversion work is always a little bit more challenging with the perspective of there's students in the buildings, and really that campus is a year-round campus. Yes. Even in the summertime, they have a number of things that are happening, so there is no downtime. So these buildings need heat, they need humidification, they need domestic hot water. So it's always a challenge when you're converting a live campus like that in such a short period of time.
And then, yeah, and then the percentage of buildings connected was the second part. Are you at?
Yeah, I'm pretty sure. Yeah, like the existing steam system no longer exists, so everything has been moved over. Okay. There's a couple small buildings on campus. I know, like the greenhouse, for example, that doesn't have. It has maybe its own little heating system, but very minor. All the significant load on campus is connected to the district heating system.
And that was one final question from a participant. Is it what percentage is the heat for the buildings, and then how much goes to sort of the farm applications? Is there? Do you have a sense of the percentage there?
Yeah, I mean, it was unclear. I mean, all the heat goes to the heating app. The farm doesn't take any direct heat. Yes. The farm takes the ash, which is a byproduct of combustion, but all the heat goes to campus operations.
Okay, and farm being sort of the research aspect of basically the work of the university, right? The mission of the university. Well, I think we've covered all the questions. That's going to bring us to conclusion of extra time. I want to thank all of our panelists for not only being available today and sharing your experience and expertise, but also the work that went into submitting for the Innovation Award. I hope, and to a question that was asked, yes, the presentations will be available as well as the streaming aspect of the webinar. So those will be made available to all registered participants. So again, congratulations. Michael, I know, brought his award. Michael, you want to sort of raise the World Cup there? He brought his Innovation Award. Kevin, you got yours handy. But so I just want to urge, any of you that are sort of on the call still, we're really interested in IDA and what you're doing. So we'd urge you, if you have a project or project, as you might say, having two Canadian in the mix, two Canadian winners. We'd love to see them for IDA Innovation 2023. It'll be presented, the awards will be presented at our 114th annual conference in Chicago in June. We really do, I think we really enjoy learning more about how our business partners, our service providers, and our members are collaborating to solve these, I think, really serious challenges for our communities, our climate, and our citizens. So I'd like to again thank all of our participants for being available, and then like to invite all of you to join us. Tanya, last slide. Please make plans to join us at Campus Energy 2023, Grapevine, Texas, end of February. I'd urge you, if you haven't yet, please make your hotel reservations. Things are filling up. We've got 150 150 presenters in sessions, panels, and expect, hopefully, good Lord willing, or inshallah, as they say, 1,100 or so attendees, and hope you'll make plans to join us there. So with that, I want to thank the IDA team for being available. Also, the call for presentations for the annual conference in Chicago, interestingly, is midnight tonight, right? So if you'd like to be considered to present at the IDA 2023, the theme of the conference is Empowering the Next Generation, which is a double entendre of our chair, David Musto from Thermo Systems. Please submit 75-word abstract. Doesn't have to be the full presentation, but just share with us what you're thinking about. And we really like to feature the good work that you're all doing. So with that, I'm going to bring this to a close and hope your team wins. And it's an exciting World Cup final. And gentlemen, excuse me, thank you again for your continued support, and congratulations on your recognition. Well deserved. So thank you all. And I think that's the conclusion. And we'll bring it to a close. Have a great day.
Thank you very
Great
much.
evening.
Thanks, Rob.
All right.
Everybody.
And
Thank
hope
you.
your team wins,
Inshallah.
whoever that may be.
Thank you.
All right.
Bye-bye.
Bye for now.